Hi. Today we are going to discuss an important property of light beams, total internal reflection. This picture explains this property. From an optical source, light beams are focused onto this, and the light beams travels from one end to the other end following a particular pattern. You all might have seen such a pattern of light. Let's discuss how this pattern is formed. Before going into the topic, let's discuss some of the basic properties of light beams. We know rays travel in straight paths unless deflected by some change in the medium. Here, a light beam is shown as traveling in this medium. When it reaches here, it hits the surface. Here, it is a plane boundary between two media. So what happens is, the ray gets reflected. This property of light is known as reflection. In order to measure the angle, we can consider an imaginary axis perpendicular to this boundary. Now we can say that this is the angle of incidence and this will be the angle of reflection. And the most attractive feature is that when reflection occurs, the angle of incidence and the angle of reflection will be equal. Now we'll consider another property of light beams, refraction. This indicates a boundary between two different media. This is medium 1 and this is medium 2. Consider a ray traveling straight through this medium 1. At this point, the light beam has to enter into the second medium. The light was expected to travel in straight line, but due to the property of the second medium, the light beam had to deviate from its original path. This phenomenon of deviating from the original path when the light beam travels from one medium to the other is known as refraction. Here also we can consider an imaginary axis commonly known as normal. So there will be an angle of incidence and the angle of refraction can also be measured from the normal. There is a particular relation between the angle of incidence and the angle of refraction. And this relation is explained by Snell's law. It can be defined as n1 sine theta 1 is equal to n2 sine theta 2. Here theta 1 represents the angle of incidence and theta 2 indicates the angle of refraction. Here we can see another two terms n1 and n2. n1 is the refractive index of the first medium and n2 is the refractive index of the second medium. What do you mean by refractive index? The refractive index can be defined as the ratio of speed of light in vacuum to that of in any other medium. The factor n is the refractive index or the index of refraction of the medium. The letter C indicates the velocity of light in vacuum and the value is approximated as 3 × 10⁸ meter per second. And the term V indicates the velocity of light in any other medium. So the velocity of light in any medium other than vacuum can be specified by the number refractive index. Every material has got its own refractive index. Air is approximated to be having 1, water 1.33, diamond 2.417, glass 1.52. Likewise, all materials have got their own refractive index value. Considering the Snell's law, we can define two different conditions. The first condition is n1 less than n2. That means the refractive index of the first medium is less when compared with that of the second medium. We are considering this is the incident ray and it is keeping the angle theta 1. When it enters into the second medium, it will deviate its path and the newer angle is termed as theta 2. With this condition n1 less than n2, keep in mind one thing, the deviation will be towards the normal. That is, the ray bent towards the normal. Similarly, we will consider the next condition, n1 greater than n2. That means the first medium is having a higher refractive index and the second medium is having a lower refractive index. In such a condition, we can see that the refracted beam deviated away from the normal. That is, with the condition n1 greater than n2, the ray will bend away from the normal. This condition is very much important when defining the phenomenon total internal reflection. As a first case, we are considering this angle of incidence and this will be the angle of refraction. We'll now consider another ray which hits the normal in a greater angle. Now this can be considered as the second angle. As we are considering this condition n1 greater than n2, the refracted beam will then be refracted away from the normal and this will be the second refracted angle. We'll consider another ray with a greater incident angle. Here I am terming it as 3. And for the incident angle 3, the refracted beam has gone even more further. We'll now think of another ray with a greater angle. According to Snell's law, if the angle of incidence is getting higher, then obviously the angle of refraction should also go high. You can see with a greater angle, the refracted beam has now passed through the boundary between these two media. Now the angle of refraction is 90 degrees. Here at this point, we can define an important term, critical angle. Critical angle is the angle of incidence at which the angle of refraction keeps 90 degrees. I repeat, critical angle is the angle of incidence at which the refracted beam travels through the boundary between these two media, or it is the angle of incidence at which the angle of refraction equals 90 degrees. We'll continue to do our experiment. We'll now fix another angle that is greater than critical angle. According to Snell's law, the angle of refraction should also go high. With the critical angle, we got the refracted beam through this boundary. So this beam will not get a provision to enter into this second medium, but rather than that, it will go into the first medium itself. By examining, we can see that the angle of incidence and the angle of refraction are equal. We have already discussed, if there is such a condition, that is the angle of incidence and the angle of the departing ray is also same, then it can be counted as reflection. So what we have seen here can be termed as total internal reflection. This is a refraction property, but it resembles a reflection property. The ray got refracted internally within the first medium itself, and that too showing the property of reflection. So it is termed as total internal reflection. So the basic requirements for obtaining total internal reflection are: the refractive index of the first medium should be greater than the refractive index of the second medium, and the angle of incidence should be greater than critical angle. For all angles greater than the critical angle, the refracted beam will be seen in the first medium itself. This phenomenon of light is used in optical communication, and there we will be using the conditions n1 greater than n2 and theta I greater than or equal to theta c. We know when the incident angle is equal to theta c, then the refracted beam will be traveling through the boundary condition. That beam can also be utilized in optical fiber communication. Thank you for watching.